Okay.
Okay, so good morning, everyone. Welcome. What's the word I'm thinking of? Labrite, maybe that's the right word for introduction, and good morning. So I'm Brian Wiley. I'm from ULEX Supercomputing Center, and with my colleagues Marta Garcia and Cedric Valenci today, we'll be giving you a very introductory presentation to parallel performance analysis and the work of the POP Center of Excellence. So we're happy to be here with the Latvian NCC, National Competence Center for HPC. And as I said, we'll be here for the next 3 mornings to cover the introductory training material with you. So these sessions are morning sessions, so we'll be covering 3 or 4 hours each day. You're on Zoom here at the moment. The sessions are being recorded, so make a note of that. But we want these sessions to be as interactive as we can, so please ask questions. Either ask the questions by writing them into Zoom itself, into the Zoom chat, or raise your hand, make yourself known, and then we can unmute you and allow you to ask a question. The materials will appear later. We don't have them online at the moment, but the website for that information is being prepared and will be available probably next week. So we have 3 mornings set up for you. This first morning is introductory material covering the concepts of parallel performance analysis and the work of the Center of Excellence, and with a few teaser examples of assessments that we have done of application performance that we think are motivating for you. And then the following days, tomorrow and on Friday, we will be going in more depth about the different tools that are available, some of the tools that are available through the Center of Excellence, focusing on profiling tomorrow, and then more detailed trace analysis on Friday. So we know that many of you are novices, that you're not so experienced or have no experience with high performance computing and parallel applications. So we'll try and keep things relatively high level. But if there are things that we mentioned that are confusing or unclear, please let us know and we'll try and address those questions as we proceed. So you'll see the schedule suggests that we have relatively long breaks between the sessions. That's an opportunity, of course, to get away from the screen, but it's also an opportunity to go into more detail about questions that may arise. So, so let me, with that, switch to my other presentation, which will be an introduction to parallel application performance engineering. Let me just see if I can switch here. There we go. So has the switch worked this time, Marta?
Yes, perfect.
Okay. Yeah. So this is material we've used for a number of tutorials and training sessions. So it's very high level and introductory. And we hope it gives you a good foundation for some of the discussion and materials that will be presented in the subsequent sessions. So performance is not a new problem. Performance has always been an issue with computers. The picture here is one of the first computers, and the developer of that computer, Charles Babbage, was already thinking about performance as a constraint, that they wished to reduce the time to get the calculations done, to get more answers more quickly. So that was the state of the affairs at the beginning, and it has never changed. People have always been looking to get more efficient, more productive use of these restricted, more challenging computational devices. For many years, it was possible to just wait, and the next generation of computer, the next generation of processor would automatically give you a performance and benefit from improved technology, from a faster clock rate, a faster ability to process individual calculations. That was the situation through the last decades. The technology is still improving. There's still Moore's law improving what can be put onto a processor, and the more transistors and components that can go into a processor benefits you in terms of what you can do with that device. But whereas initially you could just leave your program as a serial serial application, which was doing one thing at a time, for the last decade or so, it's been required to look at parallelism, to use the fact that these devices now have space to have a number of cores, a number of components on a single processor, a single die, and to use those at the same time to get overall performance benefits through improved throughput. That is a challenge because not only have the components become more complex and more difficult to use, the applications which are being built in the last years to use those are also increasing in complexity. So you have to deal with the fact that you have multiple components, that there's a hierarchy of components, it's increasingly heterogeneous, there's a network or other connections between the devices. You increasingly have graphical processing units where you have very powerful devices that need computation offloaded to them, the data offloaded to them, and then brought back. So the devices and the machines themselves are increasingly complex, and the applications have to adapt to that. They have to split their computation, distribute it over these devices, coordinate what they're doing, as well as the fact that the applications themselves are increasing in their complexity, combining physics with chemistry, with all sorts of other scientific processes. Nowadays, people talk about integrating artificial intelligence to do things during a computation. So there's always a trend to do more, and that trend tends to increase the complexity both of the applications and how they're able to use the machines, the collections of machines which are being used for these computations. Our experience has been that every time you increase the scale, there are new bottlenecks or new performance issues that are introduced. This is not saying nothing about debugging and getting the correct results, but even if the application is running correctly and you increase the number of processes or the number of threads, the number of compute nodes that are being used, typically there's another bottleneck that comes in that needs to be identified and addressed, and that's where performance analysis and performance tools have a role to play. Again, we're dealing today with an environment where there's a number of different computer architectures that have different characteristics that may be beneficial if they can be exploited. There are optimization challenges associated to distributing computation over increasingly large numbers of cores and processes, and also dealing with heterogeneity, where you're dealing with some things executing on the processor, the CPU, as well as things that are being offloaded to an accelerator device like a GPU. The individual devices themselves are complicated. They have the ability to process multiple instructions in a vector at the same time, but only if it's suitably presented to the processor as a vector with all of the data contiguously arranged. And the memory hierarchy, where you're dealing with caches and different levels of memory for bringing in large amounts of data and managing it in these computations. Those are all complexities, challenges associated with modern computers, not as well as high-performance computers, but even general computers have these issues as well. So none of this typically happens automatically or can be taken for granted. An optimization process is required to identify performance issues and identify whether the application is executing reasonably efficiently or can be improved. On the application side, the codes get more and more complex. They're increasingly beyond are challenging for small teams or individuals to maintain. Optimizing them is time consuming. Every time you change the code and try to improve it, this is an error-prone process. It's not automatically solved by using an AI to do the changes for you. You have to verify that they're done in a reasonable fashion and then it's done in a maintainable fashion. So understanding how the applications are executing, where they're spending time and what resources they're using is a critical part of application development and application optimization today and will be in the future. We like to try and simplify things by considering two different sets of factors that come into play, which we're here referring to as sequential and parallel factors. So the sequential performance factors are the things that are an aspect, even if it's a single process, a single core that we're dealing with, you need to make sure that you're doing computation in an efficient algorithm. You're benefiting from the fact that the compilers these days can do a number of optimizations for you if they are given a chance. How you effectively use the available cache and memory available to a core is important, and the compiler can help you with that. It won't always get it right, but it can show you what it's doing, and then you can verify if it's doing it efficiently or if there's something impeding its ability to do it. Also mentioned here is file I/O, getting the data in and out of the process from disk into the process, into the application itself. This is an important aspect for a serial application. It becomes even more challenging with parallel applications, but it's something that becomes increasingly challenging because you're dealing with the interaction with a shared resource. So the file system is typically not something that's dedicated to individual users, but it's something that is shared with multiple users. And then you have important interactions between who's using the file system, what they're doing at the same time as your application is running. And so that is that can be a challenge for distinguishing your application's performance from the environment in which it is running in. So all of those aspects come into serial application execution. They're compounded by parallel performance factors when you're trying to use multiple threads and multiple processes and multiple nodes where you're combining things running across large distributed systems. You have to decompose your application. You have to split the work into different parts, which are then shared and executed by different computational resources. There'll be communication involved in terms of doing that distribution, coordinating what the different processes and threads are doing, and aggregating or collating the results, typically at the end or at intermediate stages. Message passing is what is a very common way of doing that for distributed systems, or it may be something that you're doing within a single node where you can avoid explicit message passing, but you still have to coordinate what is going on. So you'll have multiple processes across nodes or within a node. Multi-threading is another technique where you have threads executing, lightweight computations executing within a node, sharing access to data, but you have to coordinate again what they're doing so that they are not overwriting each other, that they coordinate what they're doing through synchronization and locking. There are various tools available to help with this and to analyze this, and we'll see a few of them in the course of the next days, because these parallel performance factors are the ones which our tools primarily focus on and which have a key benefit for you, because understanding what's happening with a single process and on a single core, often there's a different set of tools that can help there. Often they're vendor-specific tools, but when we're dealing with distributed applications, you need additional tools that can help with this. So those are the two factors that we'll kind of discuss, but we'll mostly be in the tools that we'll present, we'll be looking at the parallel factors. Engineering a successful parallel application is a combination of a lot of different things. There's different tuning parameters in terms of how you configure the application and how you run it on the system, how you split it across nodes, how you set affinities and bindings for that. There's also important algorithms and libraries that you can benefit from, and those are a great starting point in many cases, as well as for your code using optimization flags for the compiler, and if necessary, putting in additional directives that give the compiler or the runtime system hints as to what you're trying to achieve or where it can exploit different characteristics to improve performance. There's a lot of thinking involved, but thinking is a process of analyzing, investigating what can be done, and then thinking about whether this is efficient or how it could be optimized. It's always the case that where you have measurements, these are better than guesses. So as I mentioned, with things getting increasingly complicated, it's hard to really understand how things are going to execute without having a lot of very detailed information. And having measurements will tell you how something executed and help you identify where the most important bottlenecks, the most important performance limitations can be located. They also help you when you're comparing alternatives or when you're trying to validate optimizations or changes that you've made. So just changing things and hoping for the best, expecting that to be beneficial is usually not a good strategy. You want to do a measurement after each step, compare multiple alternatives, and use that as a basis for deciding this has worked or this hasn't worked as or hasn't had the benefit that was expected. Or in many cases, you'll have a benefit to one part of the execution that might have reduced the performance in some other part, and there's a trade-off there that needs to be understood. Sometimes it's possible to generate models of parallel application executions. This is very challenging. Typically, this is a lot of work to do, and is not something that is practical in all cases. But if you have a model, it can give you hints and some insight into how you expect your application to perform. We won't consider modeling as part of this course these next few days, but models are something that can be built from measurements. So if you have a good set of measurements, the model can be built from those. So if we think about engineering, this is a multi-step process, and it's not a straightforward process with a single endpoint, but it's a cyclic process, and there's going back and forward. So if we consider 4 different steps here, shown in the circle in the center, a starting point is where you prepare your application. You're obviously going to prepare a test case that runs and ideally runs correctly. But as part of that preparation, you may also want to provide some additional information that can help with the performance analysis. This can be in the form of simple debugging information that will help the tools to identify which parts of the code, which parts of your application code are executing. Or it may be that you can exploit additional code that gets added by the compiler or by some conditional process, which will also give some additional context or some additional information. So the preparation can be an important part of getting the sorts of information that you want and the information you want out of the subsequent analysis. When the application has been prepared and you execute it for measurement, now let me switch mouse. When you run a measurement under the control of one or more performance tools, usually you have the ability to decide what is going to be collected. Sometimes you might think that just give me everything and I'll deal with it later, but that's usually not a great strategy. Usually you want to be a little bit more targeted in terms of what information you want to collect and what you're going to do with it. And you might refine that process. Often you will refine that process, but depending on what you're trying to do, different measurements are possible, and you would want to select those. So as the application executes, measurements are taken. They may be aggregated in different ways or collected for subsequent analysis. And then when it gets to the analysis stage, metrics are calculated. We'll see some of those in a moment. Those will be presented in different ways and hopefully will help you explore and identify various performance issues. And from that process, you can hopefully get some ideas as to what things might be changed or might be improved in a subsequent optimization. The optimizations are typically something that you will have to do yourself, or maybe it's changing a compile flag or bringing in a different additional library or setting a switch. There's lots of different optimizations that can be applied. Some are more straightforward than others, but after doing the optimization, you'll want to verify it by returning to the cycle and verifying that the changes you made, not only the application still runs correctly, but has benefited your application's execution performance. This isn't a complete cycle, because at each stage it may be that you decide you need to go back up and redo something. So as part of the analysis, you might find there's something missing that's important, and so you go back and do some additional measurements. And as I said, you may want to configure different measurements before you to collect different information for the analysis, or it may be that you have to go back to the preparation stage and do some additional application preparation to get more precise information and more accurate information about the parts of the application execution that's important. So this is a cycle that goes back and forward, as well as going round and round. An important rule to bear in mind is what we refer to as the 80-20 rule, or the Pareto rule. This is a simple statement that application programs typically spend roughly 80% of their time in only 20% of the code. Another way of looking at that is the reverse, or reverse corollary of that is that you can often get 80% of the possible benefit of changes by only using 20% of the effort. So the first things that you can change, if you target the right things and you target them appropriately, will often be the ones that give you the biggest bang for the buck, the biggest benefit. And as you continue, it becomes more and more difficult to get the last few percent, which in many cases is not so critical or is not so productive for you. If your main interest is science and getting scientific results, you may want to stop earlier. If you're a performance engineer and you're benchmarking and trying to get that last few percent, you'll spend a little bit longer. So know where you are on that spectrum, but recognize that focusing your efforts to regularly reanalyzing the application and looking at what can be easily improved to get benefits are often more productive than just trying to do everything and continually optimizing in an endless cycle. So don't optimize the parts of the code that don't matter. Large complicated codes won't necessarily execute everything, and not everything will matter. So identifying what is executed most frequently, what are the common cases of execution, those are the ones that will give you the most benefit if you can improve those. This was something that was identified by Donald Knuth, one of the luminaries in computer science. He's put it in his terms: if you optimize everything, you'll always be unhappy. You'll be optimizing things, spending a lot of effort in parts of the code which are not going to benefit you overall in terms of improving performance, and you'll be making the code more complicated and harder to maintain, and that will just make your life much more difficult. So keep things as simple as you can, and only target optimizations and improvements at the parts where you identify there's a benefit can be resulting from them. There's a whole range of different things that can be measured, and I'll take you through a few of those so we have a certain terminology that we can use for presenting the additional tools and discussing what they're able to do. A time interval is a duration, the time of the entire application execution, or the time for individual parts of the code, or times for individual calls to functions, for example, or times for an individual MPI send, a message send. That duration is typically what you're most interested in, but understanding how long something takes is often a factor of knowing how many or how much impact it has overall. Will also be a need to take into account how often something occurs. So how many messages are being sent, how often a function is being executed, because the more it's executed, the more messages that are sent, naturally, the longer this will take in aggregate. Likewise, parameters to different application function calls can be important. Depending on the parameter, something might execute very quickly, or it might take much longer. And one example is for a message transfer. If you're transferring a very large message, you have to expect that this will take considerably longer than a very short message. So knowing the sizes of parameters is also important, as well as how many messages are being sent, as well as to understand the overall duration of these events. From these basic measures, we can derive additional metrics. We can translate or convert them into to throughputs or rates, so how often something happens per second. And that's, or the proportion of time that's for a certain thing, how much, which proportion of data is sent at a particular point in time or between a certain pair of processes. All of those derived metrics are helpful when you're comparing things. When you're normalizing things, you compare from run to run, or different test cases, or across different systems. So in many cases, you'll be dealing with rates rather than absolute measures of what happened and when it happened. Execution time, we understand, is important. That's often what you're charged for. How often something happens, the number of times a function is called, how many messages are sent, those are I think, easy to understand metrics, but you've probably heard of and will hear of additional metrics which are perhaps less familiar to you. Things like cycles per instruction, or the reverse, the reciprocal, which is the number of instructions which are executed by for every clock cycle of the processor. That's a measure of the computational throughput of the hardware itself. If it's suitably prepared, a processor can execute multiple instructions every clock cycle. And if it's not able to do that, it's typically because there's not enough work for it to do, or it's having to do very complex things as part of that process. Another common metric is floating point operations per second, known as flops. Flops has been an important measure for many years, dealing with the floating point performance when floating point performance was a very limiting factor. Nowadays, it's less important because memory operations, the time waiting for memory and waiting for data, is often more important than the actual time for doing a floating point calculation. But flops is still important for many applications. The thing to bear in mind is that floating operations can mean different things to different people or to different tools. So depending on what is being considered, you may want to consider all of the floating point operations or just the ones related to calculation. So is the reading and the writing of a floating point variable an operation, or do you just consider the additions, the subtractions, etc.? You can also distinguish between what the hardware operations and the hardware instructions are, because some things can happen as a single instructions, other may require multiple instructions. So things like divisions are typically multiple instructions or take much longer than additions and subtractions, which are straightforward. Another important factor to bear in mind is the amount of precision, the amount of data in a data element will be a factor in how long something takes. So it used to be that 32 bits was considered standard precision, 64 bits was double precision or high precision. Often these days people are looking to exploit lower precision, half precision, so only 16 bits or maybe even 8 bits as a way of getting faster performance by trading off the amount of accuracy, the amount of precision you have in the computation versus how much data is being moved around and the computations that are being done with that data. So know what sort of operations you're dealing with when you start looking at floating point metrics. Execution time is the key thing that we're typically optimizing these days. You may argue that energy is important, and that will be an important thing in the future for sure. But the best way to reduce the amount of energy required for a computation is to just make sure that it executes more efficiently on a shorter time, because while the processors are waiting, they're also using energy, and if that's going to be a factor in terms of your overall efficiency. So wall clock time we refer to as the time from when something starts to when it finishes, as measured by your watch, or as what it would look like on a wall clock. This will include the time for all sorts of things that are going on, whether those are getting data in and out of the computation, waiting for data coming from memory, everything else that's happening on the system. So where you are sharing resources on a system with other applications, you'll be sharing those resources, and your wall clock time, the time from begin to end, will increase correspondingly. If we just look at the time which an individual process is using, that's the CPU time. And the CPU time is a more comprehensive measure of what your application is doing, because it won't include the time where your application processes were not running because something else was using those resources, or where you're waiting for I/O, for data to come in and out of the application. CPU time is also something that is applied to each resource that's being measured. So if you're using multiple cores or multiple nodes, the CPU time will typically aggregate all of those together and will be much more than the elapsed time. On the other hand, if it's just a single process that's executing, the CPU time would be less than the wall clock time, as we just mentioned. So know the difference between the wall clock time and the CPU time. Typically, wall clock time is your time to solution. That's going to be important for a number of reasons. The CPU time is important because it's typically what you're going to be charged for. The compute centers will be charging for resources based on how much time their individual applications are using. So if you're using multiple resources, you're going to be charged for those, and the aggregate CPU time will therefore be more important measure than just the wall clock time itself. Another thing to be aware of is execution time may be non-deterministic. It's going to vary from run to run by typically a small amount if it's a well-defined execution of a single application on a single resource without interference from other things. But that's not always going to be the case, because as soon as you go to the file system, as soon as you're sharing a computer net, an interconnect with other processes, there's going to be inevitable delays and variability that comes into execution times as a result of that. And that's without the additional complexity of applications themselves potentially being non-deterministic. That if your algorithm is a Monte Carlo algorithm, for example, where it's searching for a solution, it might get that solution quicker in some runs than in others based on the way it does its search. So if you're trying to compare those from multiple runs, you might see that the time varies might vary considerably. And you need to understand that and figure out how you're going to deal with that variability in understanding the measurements. It may be you have to do multiple runs, or you do an averaging of multiple runs. That will be left up to you, but typically you need to run things multiple times, at least to understand what level of variability it is. And if it's only 1 or 2%, then you can typically live with it. But if it's a larger variation from run to run, you'll need to understand that and factor that into the analysis. When we present profile information, but also other information, we're typically comparing or mentioning what we would distinguish as inclusive versus exclusive metric values. If we consider a very simple piece of code here. Function foo here is doing a little bit of computation, and then it's calling another function called bar here. If we do a measurement of foo itself, we would be timing the time from the beginning to the end of foo, the part that's marked in green here. And that would include the time that's also taken by bar, the functions that are called from inside foo. Assuming that we're also measuring the time in bar separately, we'd end up with the time being attributed to both foo and to bar in that case, unless we take an exclusive approach where we identify that bar is called from foo, and therefore we have its metrics separately. And the part of foo which doesn't include the sub-functions, the part in orange here is the part that we would consider to be the exclusive metrics for foo itself. That will help us to determine, should I spend my time looking at the performance of bar, or should I spend my time looking at and improving the performance of foo itself? Is it the orange part here that is a foo that is critical for the performance and should be improved, or is it bar that I should be looking at? So inclusive and exclusive is one way of distinguishing these two metrics, and we can exploit that in how information is presented, as we'll see later. So I'm briefly going to go through different techniques that we can use, techniques that we can use for triggering measurements, for recording measurements, and doing the analysis of the data that comes from those. So the first part of this is how we trigger measurements, and we'll consider two approaches, which I'll refer to as sampling and code instrumentation. The sampling approach, which we'll consider here first, for this, again, relatively simple piece of code, which is being executed here. And if we execute it on a single process, we can consider that we start executing main, we then start executing foo, which returns. The next time we execute, we're actually executing foo with parameter 1, which means that it also calls recursively into itself again, which ultimately returns. And then, since we're going through this 3 times, we have foo2, calling foo1, calling foo0, and then returning from those before completing. So typically, you'd be executing different functions, but just to keep things simple and have it all in one slide here, we're dealing with a recursive piece of code here. But the thing is that we would like to be able to see what is the most important part to understand the performance of. Is it the time in the orange part, the time in the green part, the time in the blue part here? And one way of doing that is to use a sampling approach where we periodically interrupt the execution and check what it's doing. We could do this in a debugger and just take some ad hoc samples, but there are better ways of doing that. So the operating system itself has mechanisms that we can use. I need to turn off the pointer here. No. If we take a sample at the beginning, we're in main. We take a sample a certain time interval later, and it tells us that we've gone into function foo, and we're at the 0th level of function foo. The third sample, we're back in main, and this goes on and on. We have multiple samples at regular intervals through the execution. Every time we have a sample and interrupt, we can check what is executing at that point, which function is being executed. But we can also use additional mechanisms to figure out what is the context for that measurement. So the sample here at time 6 would allow us to determine that we're actually we're in function foo here, but when we're executing sample 8 here, we're actually nested because function 8, this function here is executed within the context of the other 2 functions here. So we can build up information that tells us a bit more precisely what is being executed and how we got to that point of the execution. This information gives us a set of measurements here, and we have 9 measurements, which we can attribute to the red, the green, the blue parts of the code. And if we have enough of these samples, we'll get a good statistical measure of how much time was spent in the different parts of the execution. If we have only very few samples, we don't have very good statistics. So we typically would want a relatively long application execution or a high frequency of sampling, which we can typically adjust. So that's the One of the benefits of sampling is that we can adjust the sampling frequency to get more or fewer measurements if we want, and we don't need to do substantial changes to the application execution to do this. We can rely on the capabilities of the processor in most cases to get this information. Where this is lacking information is that we're not guaranteed to get all of the events that are happening here. There are things that we're missing between the points which we're observing here. So if we want to have a clearer information of what's going on, the other approach is an instrumentation approach where the code itself is instrumented in a way where every time we start executing something and finish it, we put in markers. And those markers allow us to time those events. So we'll get precise timing information at the beginning and end of each event. And that also allows us to build up this hierarchy, this structure of events. We'll see there are different ways of getting these measurements. We can get very detailed information about how things are executing here, because we can be selective about what we're measuring and what not. And for some things, that can be very important. So for things like message passing using MPI, if we want to know how many bytes are being sent, if we want to know which communicator or which receiver is data is being sent to, that parameterized information is not something we can easily get through sampling. So by instrumenting the code and having instrumentation that is collecting that information, we can get very precise information about the message passing or the lock synchronization when we're doing multi-threading. If we do that excessively, we'll have a lot of information collected, and that will be detrimental in terms of overheads, because some of these events may be very short. So we can see here we have clusters of events here that are coming very shortly after each other. So we will have a time penalty associated with that. Everything we measure has a cost to it, and we have to be aware of those costs and the trade-offs that are involved. But we can trade off getting very precise information versus getting statistical information that may be adequate for giving us insight into where to look at performance issues. When doing this instrumentation, there's different approaches, which we will see in the course of the next days. But the code can be inserted manually. So if you know what you're looking for, you can put in code instrumentation yourself. If it's to distinguish different parts of execution that are important to you, you or someone who knows the code is in the best position to do that. Or you can exploit the fact that there's a number of tools that can help with this. So the compiler is able to do forms of instrumentation of functions automatically for you. There are libraries which are provided in a way which allows us to get instrumentation from those, such as MPI or from the OpenMP runtime. So those can be used with relatively little application involvement. And there's also more comprehensive ways where the whole application gets rewritten in various ways to add different forms of instrumentation. All of those have different trade-offs. Different tools will provide those capabilities. We'll see one or two examples, and others can be investigated if necessary. But the key thing here is that there's a trade-off. There's a trade-off in the accuracy of the measurements and how reliable those measurements are as a result. So if we're doing lots of measurements of how the application is executing, there's a cost to that. Every measurement needs time. Every measurement needs a place to store the results, and that will be taking time and resources away from what the application would be doing on its own. If you do too many measurements, or if you do measurements at the inappropriate times, then this will potentially perturb the application. It will change the application execution behavior that you're trying to understand. Again, some of this is unavoidable, that whenever the instrumentation is doing anything, whether it's sampling or whether it's code instrumentation, if it's checking the call stack, if it's storing some results, it's going to be accessing memory, and it will be changing your memory access patterns as a result. There's also trade-offs in terms of how much information is collected. If you're trying to collect lots of measurements at the same time or very precise information, this can often be more costly than just getting some very coarse information that is enough to help localize the problem, and then perhaps get more detailed information for parts that are really important and you need to understand in more detail. There's also a trade-off in terms of how measurements are processed. So simply storing the information for later analysis might be relatively cheap in terms of time, but is more expensive in terms of storage. Or you can do more processing, taking more time, but reducing the amount of storage that's required. So again, there's a trade-off there, a trade-off between the accuracy of the things that you're measuring and the expressiveness, the reliability of the data that you're collecting as a result. We've already started discussing some of the things that we're going to do with these measurements. So how is the data being recorded? And there's two main ways of recording data. One which we'll refer to as profiling, where we're summarizing information. The other which is tracing, where we're storing things for later analysis. So in a profile summary, we take the measurements, whether we're dealing with time measurements or counts of different aspects, and we're aggregating them together. The typical aggregation is just to total things up. So you get the total time, the total data transfer, the total number of function calls. But it may be that there are other metrics that are important, such as just the maximum data transferred or the maximum time. The information that is summarized can be summarized in different ways. Typically, it will be summarized according to the function in which is being executed, or the set of functions that are on the call stack that are being executed at the point where you're currently executing, or you can go down to higher resolution and look at parallel loops or individual loops of execution if you want that more fine-grained resolution where the metrics apply. We would also typically have information separately for each process and thread. So if we collect information for each process and the thread, we can then compare them at the end of the execution, and we can then look at which ones are they all executing and taking the same time, or are there significant differences between them in terms of what they're doing or the time that they're taking. So this profiling is a summarization of events. Again, it's reducing the information substantially, avoiding needing to store it all for later analysis. We can store things in simple profiles or more complex profiles, call path profiles, which give us the execution context. That execution context can be important for distinguishing where a function is called in different ways in different parts of the execution. So if we look at a message passing function like an MPI barrier, for example, it may be called at a number of different parts of the code. And where it's called in the initialization might not be as important as where it's called in the main solver. If it may be called more frequently there, it may be more costly there because of load balance or other aspects that are coming into play. So knowing not just what functions are being called, but where they're being called is an important part of the analysis, and is part of what can be provided in the profiles. We can also look at very specific profiles that are just looking at MPI information, or just looking at OpenMP threading, or where we're explicitly comparing a profile of what's happening on one process with others or between threads. So there are lots of different ways of applying this profiling or looking at the profiles information. The tracing approach avoids the need to do as much processing during the execution when we're doing the measurement. It is capturing the information, storing it in memory, storing it in files at the end of execution, which allows us to do a more comprehensive analysis later. For every event, whether it's the entering and leave of a specific part of the execution, or the send and receive of a message, for example, we have those events that are being triggered. We can record the time of those events. We can record where they occurred and the additional parameters that are associated with them. So if it's an MPI communicator involved, if there's an appropriate sender or receiver, we can capture all of that information in the trace. The trace will typically be collected for each thread of execution and for each process, and then we can build up a model of how these events occurred. We have a timestamp for each of them. We have a time-ordered, chronologically ordered sequence of event records, for each thread and what it was doing. A quick example of that is we have two processes here, process A and process B, one sending data to the other. When we get events from those, we'll have events which say when we're entering those functions and when they're sending and receiving the data. Those events trigger the monitoring system, which takes timestamps for those events. If these are events on different compute nodes, they will be unsynchronized times typically, and we'll need to do some post-processing to figure out exactly how the timestamps compare between one event, between one node and another. But we have a set of locally timestamp events on each process or each thread, and then those events are at the end of execution, the events that will be written to a file and get merged for subsequent analysis. So we have, at the end, we have a merged sequence of events that tells us what each process and thread was doing, when something was started on process A, when it did the send to B, and when that message was received. So this will allow us to relate how those events are related and figure out what was the transfer time, for example. Or knowing how much data was transferred, we can look at the transfer rate for data between process A and process B. We'll see examples of those later, but there's an important trade-off here because we are trading off the information that we are processing during measurement with what we collect and can process later. The traces have preserved the detailed temporal and spatial relationships between the events, as well as all the associated context that allows us to reconstruct the application behavior and do very comprehensive analyses of these events. And from this information, of course, we can later reconstruct a profile by just summarizing everything together again. But these traces have the disadvantage that they very quickly become very large. The longer an application executes, the more events that are being collected, the more samples that are being stored in the trace, the more that will affect the size of an individual trace for a thread or a process. And if we're collecting the information for a large parallel application with many processes, many threads, then we'll have another dimension which is becoming potentially very large. So we have two reasons for which the traces will become increasingly large, and we can only partially control that by reducing the amount of information that's stored in the trace. So we would need to be careful about what the trade-offs are here. Another way we could potentially think we can get larger traces is by when we run out of memory for storing the trace in memory in a buffer, we could write that buffer to file and then clear it and then continue. But every time we go to the file system, this is typically very large perturbation of the execution. And so we want to be careful to avoid that. Typically, we want to store everything or as much as possible in memory during measurement so that we only write traces and go to the file system at the very end. So that's the key trade-off here we have between what is stored in profiles and what is stored in traces. Analysis can be done, as we have discussed, a certain amount can be done online during measurement. Most of the analysis we'll probably end up doing offline because that way we can take more time and we can do more analyses than we could typically do during the measurement itself. So while we can aggregate local profiles, that's straightforward to do, we typically don't collect information into a single profile from all the processes and threads because that would involve additional communication and additional exchange of information. We can do that at the very end of execution, but we don't want to do that during the measurement phase of the execution itself. Whereas when it comes to offline analysis, we have much more time, we can do much more extensive analyses. And one of the analyses which we'll discuss is a replay of the application execution of the events that have been recorded in the trace. Everything is there that would allow us to reconstruct the execution and figure out what are the waiting times, what are the delays involved, and what are the things that were causing those delays. So there are different ways of doing these presentations. We'll see some more textual approaches as well as some more graphical approaches. One of the graphical approaches, which I'll just mention here, is a timeline visualization where the events that we stored in our trace tell us that we have two processes, A and B here, executing for a period of time. Where we have an event on process A, we can mark that, as well as the event on process B. And where we have a message being transferred, we know at what time it was initiated on one process, what time it was received on the other, and therefore we can draw a line or something that indicates the message transfer between those. So this can be a very insightful way of understanding complex interactions between processes and threads, giving an overview of what each process is doing. But if you have many processes and many threads, these timeline visualizations will also become challenging to present and to interpret. So I've quickly gone through a number of techniques here, which we'll discuss and we'll see in the individual tools that we'll focus on later. There's no individual solution here that's going to be perfect in all situations. So depending on what you're trying to do, what information you need, you will want to use different tools and use different setups, do different amounts of preparation and instrumentation of the code to get the information that you need. An analogy which we're using here is if you're doing something very simple like digging a space for flowers in the garden, a simple tool might be adequate to do everything. But if you're trying to do something that is a little bit more advanced, you'll need to bring in additional tools that are more suited to doing different tasks. And in your garden and in a very localized environment, you may have all of those tools available and you can take the time to learn and apply those appropriately. But when you're dealing with larger and more complicated systems like the HPC systems today, there's a lot of complexity there, a lot of things going on, and it becomes much more challenging to use the tools and to understand the system. So there are tools which are available, which are much more capable. These are more heavy duty and more comprehensive than the sorts of things that you might develop or use yourself. But it's unreasonable to expect that everyone becomes an expert in using all of these tools or even individual tools here. So that's where additional experts, performance analysts, performance engineers come into play that can provide additional advice into which tools to employ at different stages and to get different information from them to apply to your application execution. So bear that in mind. Consider the fact that there are different tools. We'll give you a little bit of insight into some of the tools that are available in the POP Center of Excellence, but we're not going to cover everything here. We'll give you just a starting point. So just to briefly run through what we might consider a typical performance analysis procedure. Do I have a performance problem? That's for you to decide, and you can decide that based on how long something took to execute. Maybe you have some speed up information comparing an execution on one process with two or with multiple nodes, or comparing different execution configurations. That might help you understand if it's good enough or whether you need to know more. If you think you need to know more, you want to figure out what is the bottleneck. Is it something on the computation side? Is it something related to communication? Or maybe it's something else. It's related to file I/O or something else that is an important factor. There are different profiles that can help you, or different tools can give you information about the MPI behavior, the message passing, OpenMP threading. Basic profiles can give you that level of breakdown, or you may want to figure out something beyond that. Not just, I have an MPI problem or I have a synchronization problem, but which part of the execution is it coming from? Which part of the code? And not just, is it part of the solver or the initialization, but give me some detailed information of which part of the solver or which loop is responsible for this. And then, why is it there? What are the other metrics that I can look at? Not just the time, but how often something is called, or other hardware counters that might tell us something about the memory behavior. All of those are additional aspects that we might want to collect to give us more understanding about why the problem is manifesting in the way it is. And we might also want to collect traces and get more detailed information just about parts of the execution, which would allow us to keep the traces more manageable. And another aspect is not just the performance of one part a single process, but how things change when we deal with multiple processes or we use multiple nodes. And so comparing things, looking at imbalance across processes, across threads, comparing profiles at different sizes, that's another aspect that can be brought in to address a different set of issues. So just to summarize here, this is very introductory material. I'm expecting that many of you are already familiar with this, but it's important that we have a common terminology and understanding. This is material that comes from the Virtual Institute for High Productivity Supercomputing, which is a collaboration, a partnership of a number of organizations. I think there's 15 or 16 shown by their logos here at the bottom. The presenters here today are all part of the VIHPS, and the VIHPS is typically where we bring together the training with our tools. The VIHPS, the website URL is on the page here, has been running here. We're actually celebrating 20th anniversary next year, so we're almost at 20 years, addressing on how to improve the quality and accelerate the development process of complex application simulation codes on highly parallel computer systems. We have a number of tools provided by the different partners. We're going to focus on a subset of those tools in the next day or so. You'll see examples of them later today, and then we'll go into some of them in more detail tomorrow and on Friday. There's lots of details about all of the tools in the VIHPS ends in our VIHPS tools guide, which is available from the website, which was listed earlier. These are some of the other tools that we're not covering, that go into modeling, that go into correctness checking, that are very specific for different aspects. There's a summary information, a couple of pages describing them, what they provide and what programming paradigms they apply to in the tools guide. So I refer you there for further information if need be. But we have, as I said, a set of tools that are available that can be applied at different stages of the application development process. Some of them are more related to debugging and error and correctness checking. Those are tools on the left-hand side of this diagram here. The ones we'll be focusing on in the next few days and today are tools which are looking at profiling and trace analysis. So those are the ones that we'll be looking at more detail. But this set of tools that we provide, most of them are open source. There's a couple of commercial tools from some of the partners that can be advantageous as well. There's a whole ecosystem of different tools that are available and can be applied, and we think you should be aware of them. The tools are not magic, they don't do everything, but they can help you to understand how your parallel code executes and when and where it's necessary to work on various aspects such as performance issues. So use the tools when they're available, understand how to make use of them and when to apply them, and then you'll get the best benefit and get the most productive use of these increasingly challenging computer systems and increasingly complex parallel applications. We provide a number of training events where we present the different tools. The best events are the ones where people get a chance to bring along and work with their own codes, so we can analyze and tune the codes together with you. These are known as tuning workshops. We've done a number of tuning workshops over the years. Just this last year, or the last few months, we've done events in Barcelona and in Durham in England. We have another event that's coming up later in the summer, at the end of the summer. That's a tuning event in Göttingen. So I think that's registration is not yet open for that, but that's something where you would have an opportunity to come along with your application and learn how to use the tools and benefit from using the tools with your own application code. We're also working on preparing a number of other events later in the year. We're struggling getting the one in Jülich organized because the system is very new and it's not fully set up yet. But we're already scheduling events for next year. Some of those events are also ones that are advertised and available on the VIHPS website and could be of interest to you. But if there's an event if there's not an event here which is ideal for you, look out for other events which are advertised, or contact us if you'd be interested in hosting such an event yourself at your organization, because we're always looking for the opportunity to come and work with you to apply and benefit from using our tools. So I think that's my last slide.